Understanding augmented reality tracking. Understanding augmented reality tracking. Augmented reality, AR, has swiftly emerged as a transformative technology, blurring the lines between the digital and physical worlds. It has found applications in various domains, from entertainment and gaming to education and industrial training. At the heart of this immersive experience lies a critical component called AR tracking, which enables virtual objects to interact convincingly with the real world. In this article, we will delve into the depths of augmented reality tracking, exploring its types, underlying technologies, challenges, and future potential. The essence of AR tracking. This foundational technology is what allows virtual objects to appear as if they exist in the same space as the real world. Without accurate tracking, the illusion of augmented reality falls apart, disrupting the immersion and experience for users. Types of AR tracking. There are various methods of AR tracking, each with its own strengths and weaknesses. The choice of tracking method depends on factors such as the intended application, the available hardware, and the level of accuracy required. Here are some common types of AR tracking. 1. Marker-based tracking. This method involves using predefined markers, often in the form of QR codes or fiducial markers, placed in the environment. The AR system detects and recognizes these markers to determine the device's position and orientation. While marker-based tracking is relatively simple to implement, it requires a clear line of sight to the markers and may not work well in dynamic environments. SLAM doesn't rely on markers, making it suitable for environments where markers cannot be placed. It's widely used in applications like navigation and robotics, but its computational intensity can be a challenge for mobile devices. 3. Image-based tracking. In this approach, the AR system tracks features in the environment, such as distinct patterns or objects. By comparing the real-time camera feed with a reference image, the system calculates the device's pose. Image-based tracking offers flexibility in terms of the tracked objects but can struggle in low light conditions or with repetitive patterns. 4. LiDAR and depth sensor tracking. Leveraging technologies like LiDAR and depth sensors, this method measures the distance between the device and objects in the environment. This data is used to create a detailed depth map, which aids in accurate tracking even in complex surroundings. LiDAR and depth sensor tracking are becoming more prevalent in our devices, but cost and compatibility remain considerations. Underlying technologies. Several underlying technologies contribute to the success of AR tracking. 1. Computer vision. AR tracking heavily relies on computer vision techniques, such as feature detection, optical flow, and object recognition. These methods allow the system to interpret the camera feed and identify distinct points or objects in the environment. 2. Sensor fusion. AR systems often combine data from multiple sensors, such as accelerometers, gyroscopes, and magnetometers, to estimate the device's orientation and position. This process, known as sensor fusion, enhances tracking accuracy and robustness. 3. Machine learning. Machine learning algorithms play a vital role in AR tracking, aiding in tasks like object recognition and pose estimation. Deep learning models can be trained on large datasets to improve the system's ability to identify and track objects accurately. 4. Inertial measurement units, IMUs. IMUs consist of accelerometers and gyroscopes that measure changes in acceleration and rotational rate. By integrating this data over time, our systems can estimate the device's motion and orientation. Challenges in AR tracking. While AR tracking has come a long way, several challenges persist, influencing the technology's effectiveness and user experience. 1. Environmental variability. Real-world environments are complex and dynamic, with varying lighting conditions, textures, and objects. Tracking systems need to account for these changes to provide consistent and accurate results. 2. Latency. Our tracking systems must operate in real time to maintain the illusion of interaction between virtual and real objects. Latency, even in milliseconds, can disrupt the immersive experience and lead to discomfort. 3. Hardware limitations. The effectiveness of our tracking is closely tied to the capabilities of the device's hardware. High-quality cameras, sensors, and processing power are essential for accurate and smooth tracking. 4. Occlusion. Occlusion occurs when virtual objects are blocked from view by real-world objects. Handling occlusion convincingly is a challenge, as virtual objects must appear to move realistically in relation to occluding objects. 5. Scale and stability. Ensuring that virtual objects maintain their size and position relative to the real world is crucial for a seamless experience. Sudden changes in tracking or device movement can lead to objects appearing unstable or out of place. The future of our tracking. As technology continues to evolve, the future of our tracking holds exciting possibilities. 1. 5 grams integration. The rollout of 5 grams networks could enhance our tracking by enabling faster data transfer and reducing latency. This is particularly significant for cloud-based experiences, where real-time tracking information can be offloaded to powerful remote servers. 4. Wearable AR devices. The development of lightweight and powerful AR glasses could revolutionize our tracking. These devices would free up users' hands and provide a more immersive experience by aligning virtual objects with the user's line of sight. Overcoming challenges for enhanced AR tracking. As augmented reality, AR, continues its march into various aspects of our lives, refining our tracking technology becomes essential to provide users with immersive and consistent experiences. While we have discussed the challenges of our tracking, it's equally important to explore the strategies and innovations that are being employed to overcome these hurdles. Environmental understanding and adaptation. One of the primary challenges in our tracking is dealing with the variability of real-world environments. Lighting conditions, textures, and the presence of dynamic objects can all affect the accuracy of tracking. To address this, researchers are focusing on improving the environmental understanding capabilities of our systems. Advanced computer vision techniques, such as semantic segmentation, enable our devices to identify different objects in the environment.